Hello everyone. So in the previous videos we saw that the problems related to the heat exchangers are of two types in our course, in our coverage, that one is analysis, another is the design problem. In the last video we saw that if it is an analysis problem, then how we can deal with it. Now come to the design problem. So in the design problem, how can we identify a design problem is so how can we identify the design problem is uh, we will see that in the design in the problem there is no heat exchanger size is given. So basically you have to find the size of the heat exchanger. So let's see this problem, that how the problem proceeds. So the benzene is used for the manufacture of detergent. A double pipe heat exchanger must be sized to exchange heat benzene between benzene and water. The benzene flow rate is given, which is 1.26 kg per second, and it is to be heated from 23.9 degrees Celsius to 37.8 degrees Celsius. The water is available at 60 degrees Celsius, and select an appropriate heat exchanger and determine the required water flow rate. So we can identify that what are the given information here and what is required. So the required is that the benzene is to be heated from 23.9 degrees Celsius to 37.8 degree Celsius. So we start with the same in the same manner that we write down the properties. So the properties, if since the inlet and exit temperature of water is not given but for the benzene is given, so for the property purpose the mean temperature of the benzene can be found from these two values. As for the water, we can choose the average between the inlet temperature of water and the inlet temperature of benzene. Okay, so the property we can find out from the table for the at the mean temperature, and then we see that what are the falling factors for benzene and other fluid water. So the falling factors also we can note from the table that the benzene falling factor is this and the water falling factor is this. Okay, so how we can proceed in this problem, and what are our design uh, criteria and design procedure and its steps. Okay. So this problem which tells us that size, select an appropriate heat exchanger and determine the required water flow rate. So it is not telling us that you size the double pipe heat exchanger. So how do we know the first of all that what kind of heat exchanger is suitable for this? It can be double pipe, it can be shell and tube, and it can be plate and frame heat exchanger. So we do not know that what kind of heat exchanger is suitable for any kind of application. So it depends upon our experience, how much experience we have, and based on that we can say that what type of heat exchanger can be suitable for the given condition. And so, but as in experience, we have to start with the double pipe heat exchanger. That we are going to start with the double pipe heat exchanger, and if it meets your requirement, then fine. If and it doesn't meet your requirement, then you go for higher capacity or lower capacity heat exchanger. For higher capacity heat exchanger, you can go for shell and tube heat exchanger, shell and tube type of heat exchanger. Okay. So then the second question is that which fluid you will flow inside the tube and which fluid you will flow in the annulus part. So here we have a certain criteria for routing the fluid. So the one of the criteria is the falling factor, and other criteria are temperature and pressure. So here we list the different factors that we take into account while deciding that which fluid we should flow inside. So so these are the different factors: corrosion, falling factor, temperature, viscosity, stream flow rate, pressure, and then viscosity. So based on the corrosion, nature of the fluid corrosion. So the more corrosive fluid should be put inside the tube and the less corrosive should be put annulus side. The reason is that if the tubes are corroded, then the tubes can be replaced. And when the fluid is inside the tube, it will corrode only tubes. And if it is outside in the annulus part, so it will corrode tube as well as it will corrode the annulus part also, outer pipe also. So better to put the corrosive fluid inside the tube. The same thing applied to the falling also. If the fluid is more prone to falling, then the fluid which tends to fall more should be put inside the tube. The reason is same, that if it is inside the tube, it will fall only at the tube surface, and if it is outside, then it will fall tube surface as well as it will fall the annulus surface, outside pipe surface also. The third criteria is the fluid temperature. So the higher temperature fluid should be put inside the tube, and that is for your safety reason also, and that is for your losses also, to minimize the losses also. Because if the temperature is low for the outer pipe, then the losses will be lower. Viscosity, this is related to the pressure drop. So, and this is related to the surface area. So if the fluid is put inside the tube, then the fluid will have less contact surface area as compared to the when you put the fluid in the annulus part. If it is in the annulus, then it will have more contact surface area and it will cause more friction losses. So better to put the fluid with higher viscosity inside the tube. Now the flow rate. The fluid which have the higher flow rate should be put inside the annulus, and this is because the cross sectional area of the annulus usually it come out to be more as compared to the cross sectional area of the inner pipe. So the higher cross sectional area can accommodate more flow rate or high flow rate. Pressure range. If the fluid under high pressure, then it should be put inside the tube for the safety reasons. So it will have the outside fluid and as well as it will have the pipe outside the tube to protect it. And the velocity. So both side, either it is in the tube side or it is in the annulus side, in both cases the optimal velocity condition should be followed or should be maintained. Now based on these criteria, you have to choose that what is your dominant criteria, and on basis on what criteria you want to design your heat exchanger. So starting with our assumption that it is steady state as we did before, and the benzene properties you can calculate at the mean temperature which is given, and the water properties are evaluated at the inlet and outlet temperature. So but initially you can assume any temperature for the water properties. Okay, so you calculated the properties and for water and for benzene, and then we calculated the flow area. We calculated the mass flow rate for the both fluid. So mass flow rate, how do we calculate the mass? Mass flow rate is given already. Mass flow rate is given. I'm sorry. So we have the properties and we have the mass flow rate. And now we are looking for the size to find out the tube size. So first of all, we will see that what size of the tube should be chosen. So what we have the criteria with us is that the flow velocity inside the tube should be economical. So out of these two, so based on these criteria, out of the several factors, you have to decide that which factor you are taking to decide that which fluid should go inside the tube. So here in this example, we are taking that the benzene, which is have the higher falling factor 1.76 as compared to the water 1.32. So the benzene we are taking inside the tube. We are taking inside the tube, and so the benzene, when we are taking the benzene inside the tube, now we can find out. So based on the benzene mass flow rate, and which is a cold fluid, we can find out that what is the minimum area and what is the maximum area. So this is the minimum area that we need as per the economic velocity, and this is the minimum area that we need as per the economic velocity. So, so the minimum area 5.18 10 power minus 4 and the maximum area 1.05 10 to the power minus 3. So this you can go to the standards of the type M copper tubing and you can see that what standard is falling in between. So we select the heat exchanger for that, and this heat exchanger can be selected for this flow area. So the flow area is between 1.05 and 5.018. So in this case the flow area is 8.45 10 to the power minus 4, so which is falling in between this area 5.18 and 1.05 10 to the power minus 3. So it is falling in this area. So this is our this can be the one combination of for the heat exchanger. So remember, so we selected the inner. As for the outer, it can be 2 nominal, it can be 2.5 nominal, it can be any. So just 2 and 1/4 nominal, this is just one choice. So you can choose, for example, 2.5 multiplied by 1.25 for your heat exchanger. But this is what they selected as the initial selection. So if we can find out the flow area for the pipe side, and we can find out the flow area for the annulus side for this given heat exchanger. And now we can find out the velocities because we have the density, and we can find out the mass flow rate for the warm fluid, which is benzene. So remember, in the problem the mass flow rate for the benzene was not given. The mass flow rate for the benzene was given, and the water was not given. So here we can calculate the mass flow rate for the water as well. So this is the mass flow rate for the warmer fluid, which is water, and which come out to be 1.96 kg per second. Okay, so the next step is to calculate the hydraulic diameter and equivalent diameter for your heat exchanger. So we are following the steps like A, B, C, D, E, and the next step is to calculate the Reynolds number out of the velocity and check whether it is laminar or turbulent. So it is turbulent in both cases, and then use the turbulent correlations for Nusselt number to find out the Nusselt number for both cases, and then find out the heat transfer coefficient, inner side heat transfer coefficient, annulus side heat transfer coefficient, and with the help of this inner side heat transfer coefficient calculate the heat transfer coefficient for the pipe, which come out to be 1454 watt per meter square Kelvin, and then find out the overall heat transfer coefficient, so which come out to be 1232 watt per meter square Kelvin. So now we have the overall heat transfer coefficient, and then we can have the heat balance. So when we have the heat balance, so we have the two temperatures T2 and T1. So this is for benzene, and the same Q is equal to the QW. So the rate of heat transfer for the cold fluid is equal to the rate of heat transfer for the warm fluid. So for the cold fluid we can calculate, which come out to be 3.05 10 power 4 watt, and when you substitute this equal to QW, and then we can find the outlet temperature for the water, which come out to be 56.3 degree Celsius. So now we know the outlet temperatures also. So we know the outlet temperature, we know the rate of heat transfer, and we know the overall heat transfer coefficient. So what we don't know until now is the how much is the length of the heat exchanger required, because we know the inner pipe diameter, and we know the inner pipe standard, we know the outer pipe standard, and now we need to know that the length of the heat exchanger, how much it should be required. Okay, so with the help of the temperatures that we just calculated, we can find that how much is the log mean temperature difference. So here we can decide that what kind of flow arrangement we going to have. So we are having the counter flow arrangement, and we can calculate the log mean temperature difference for the counter flow. And then we know the falling factors for inner side and outer side also. So we can revise the heat transfer coefficient, which come out to be 891.5 watt per meter square Kelvin after taking into account the falling factors. So now we know the overall heat transfer coefficient, we know the rate of heat transfer here, and we know the log mean temperature difference. So when we substitute these values into this expression, so we can find the area required for the heat exchanger. So this is the area required for the heat exchanger, 1.267 meter square. And we know that the area required is pi ODP multiplied by L. So with this formula we can find out that how much is the length of the heat exchanger required. So the length of the heat exchanger required is 11.52 meter. So if it is too long, then you can have three heat exchangers of 4.57 meter long, so you can add them in series. So the length of the heat exchanger is required. So until now we know the inner diameter and outer diameter of the pipe. So basically we know the pipe standard, we know the annulus standard, outer pipe standard, and we know the length. So the heat exchanger sizing is complete now, and we know the outlet temperature of both fluids, and we know the overall heat transfer coefficient and the rate of heat transfer. The only thing left is now calculation for the pressure drop. So for the pressure drop we need to calculate the Reynolds number, and based on epsilon over IDP and Reynolds number we can find what is our heat transfer coefficient for both side, like for the pipe side and for the annulus side, and then we will use the pressure drop formula to find out the pressure drop in this case. So we have almost completed this problem. So we have everything. So we know the diameter of the pipe now, we know the diameter of the annulus now, we know the length of the heat exchanger, we know the exit temperatures, outlet temperatures of both fluid, and we know how much is the pressure drop for the pipe side and for the annulus side. Okay, so if we summarize this, that when the heat exchanger was new, that when we did not take into account the falling factors, so this is our performance, and when we take into account the falling factors, this is our performance. Okay. So what we can take from these results and from this design analysis, that the length 11.52 required under the condition of this problem, right? So this is the length that we required for the heat exchanger, and we maintain the economic velocity for the flow. So we maintain the economic velocity in the heat exchanger. So the economic velocity we choose is 1.83 meter per second. So if you choose the higher velocity, then the length will be reduced. So the required length will be reduced. So you can go to the upper limit of the economic velocity, and you can see that how much is the pressure drop. So there are constraints related to the pressure drop also. So if the pressure drop is within that constraint, so we can choose higher velocity. So this is just the design options. We can go for higher velocity, and we can basically reduce the length a little bit. So, and we know that when the heat exchanger is new, the overall heat transfer coefficient is higher, and when we take into account the falling factor, the overall heat transfer coefficient is reduced. So here we know that the falling factor effects can only come into picture when the heat exchanger is old. So if it is older than 1 year, then only we take into account the falling factors. If the heat exchanger is new, then no need to consider the falling factor for the new heat exchanger. So this is here we finish this chapter, double pipe heat exchanger. So we covered the fundamentals, as well as we covered the two methods, LMTD method and ENTU method, and we covered the tutorial problems, that is the analysis problem and the design problem. So if you have further questions, then we can discuss in the interactive sessions Tuesday and Thursday about and you need any clarification, we can discuss there. So the two examples I explained in my lectures, but other problems are related to the analysis and related to the design, you can practice from the book. Thank you so much.